Well, so in the last lecture, we studied Quasi-Newton methods, and I ended that lecture with a promise that the deep theory in which the great properties of Quasi-Newton methods are sort of established, we will discuss some of that in this lecture. So in this lecture, we talk about the theory of Quasi-Newton methods. First, we talk about the generalized rank 2 update, and then we talk about the two major properties, two properties to talk about. One is the inverse Hessian construction over iterations, and the other is the continued positive definiteness over iterations. So starting with the generalized form of the rank 2 update. So in the rank 1 update, we got four products, four outer products: PK transpose, BK into PK transpose, then PK transpose BK, and BK transpose BK. So basically, it is the four outer products between two vectors. This with itself, this with this with this, and this with itself. These are the four terms that we got in the update along with BK itself, the previous inverse Hessian estimate. So now, in that expression, in the four outer products, for the four outer products, the coefficient was the same. Okay. Now, if we allow the coefficients to be different, but insist on the symmetry of the update matrix, which is necessary, then rather than a single constant ak, we will get b minus c d. This minus c could have been put as c, that's not a problem. In that case, its final expression would be negative of what we are getting. Okay, but this and this, these two terms of diagonal terms should be same. So since this is 2 by 2 and these two are separated two vectors and their transposes are here, so this is a rank 2 update. Okay, and now when we open out this product, we get this. So the same four terms, PK transpose here, BK transpose here, its transpose, that is PK transpose BK here, and BK transpose BK here. The same four terms which were there in the rank 1 correction, the same four terms here we get, but rather than with all the same coefficients A, here we get B minus C, and D. Now, the way we try to fix the rank 1 update, or for that matter any update like this, by insisting on this matrix operating on the current step QK to give PK correctly. The same thing here also we do. So we say that this matrix times QK should be PK. Okay. So we multiply this with QK and equate it to PK. So multiply that with QK, and what we do in that, the product will be linear combination of two vectors, PK and BKQK, these two vectors. We keep them separate. So this will be BKQK. So we keep it here with BKQK, this coefficient 1. This will give us PK. Along with that, in the coefficient, you will have B PK transpose QK, which is a scalar. So B PK transpose QK. That and its transpose is the same thing. From here, we will get the vector as BKQK. The scalar coefficient will be minus C pk transpose qk, and that is why it is here minus C pk transpose qk, and the vector will be bkqk. And from here the vector will be pk, that is why it is here, and the scalar coefficient will be minus C times qk transpose bkqk, that is here. And here, as you multiply this with qk, qk transpose bkqk with d will appear as the scalar coefficient, which is here, and the vector is bkqk, which is here. And this product will be equal to pk, as we wanted. So now, for this to be an identity, okay, that is, for whatever pk and qk we give, this should hold. For that, the coefficients of pk on both sides and the coefficients of bkqk on both sides should be same. So here the coefficient of pk is 1, and here the coefficient of pk is this much. So these two should be equal. On this side, the coefficient of bkqk is 0. On this side, the coefficient of bkqk is this much. So these two should be 0. From here, we can solve for b in terms of c. From here, we can solve for d in terms of c. So both b and d get expressed in terms of c. So one free parameter remains. Okay. And that you expect, because in rank 1 correction, there was one free parameter which got spent completely, okay, in fixing the first necessary primary condition. Okay. For here in the rank 2, we actually will end up spending two independent parameters to fix the update. And that is why the third parameter that we have taken is remaining free in our hand. And we can choose that particular parameter. So we will choose when we want. Right now, let us continue with that. Putting these values of B and D in terms of C in the original matrix, we get this. Basically, we have put that B in terms of C and D in terms of C. So, and this is the original C as it is. Okay. So, this 1 plus something and this 1 minus something, these two terms are here and here. And this is the original C as it was in the coefficient of these terms. Okay. So we have fixed the rank 2 update up to one free parameter, which can be varied continuously, 0.1, 0.2, 0.3, 0.4, whatever you want. Okay. And we get different update formula. So in Broaden family of methods, we have already seen that we have got a free parameter, that is phi. That free parameter phi and this free parameter c are actually related like this. You can put this here, c equal to phi by this, and then separate out all the phi terms and other terms. You will find that you get this as bk plus, you will get this as 1 minus phi into DFP update plus phi into BFGS update. You will get this equality as you put this. Okay. And for phi equal to 0, which means C equal to 0, you get the DFP update. For phi equal to 1, which means C equal to 1 by QK transpose PK, you will get the BFGS update. And the rank 1 update you will get for this particular value of C. Okay. And this also you can check. This will fit exactly. And we proceed here. The first property that we study is the inverse Hessian construction property. Okay. And that is actually here, the property 3 here. Okay. that is bk plus 1 should operate like the inverse Hessian for all the previous directions, previous steps. Okay, but on the way to that, we also establish two conjugacy properties. One of the steps in x and the other in steps in the gradient. Okay. So these things we will establish on the convex quadratic problem, that is constant positive definite, constant positive definite. This should be definite, not defined. Constant positive definite Hessian H. Okay. For that, these properties will hold. That does not mean something very limited, because you will say that no, we actually want to minimize general functions. So what will happen is that general functions also, with enough iterations passed, will approach its minimum point where locally it will behave like a convex quadratic function. So in later iterations, near the minimum point, all functions will behave like a convex quadratic function. Okay, so that should not be a big problem. So this is the strength actually. Okay, so these properties are relevant for general functions near a minimum point. So operating bk plus 1 in terms of C on qi. By operating it on qk, we evaluated it. Now we operate this on qi, the old steps. Okay, I mean any step, which I mean till now, old or the current. So as we operate that, it is just matrix vector product. We just multiply it. Okay. So as you just multiply with qi, you get bkqi, and the other things you can reorganize a little so that qi does not have to sit inside, because when you have a term like pk transpose in the matrix and you multiply it with qi on the right side, then out of that pk transpose, pk transpose qi becomes a scalar which has been put here, and the first pk remains as the vector component of it, so that has been put outside. Okay, so the first one is b pk transpose. So this thing by this thing is b, and out of the pk transpose, the pk transpose multiplies with qi, gives a scalar, and the first pk sits here. Like that has been done with all the other terms also. Okay, and then again we reorganize them in such a manner that all the terms with pk are put together, all the terms with bkqk are put together. So this whole thing is scalar, this whole thing is scalar. This is a vector, this is a vector, and of course bkqi is a vector. So this thing is actually a linear combination of three vectors. One is bkqi with coefficient 1, the other is pk with this coefficient, and the other is bkqk with this coefficient. So for I equal to k, it is trivially true that bk plus 1 qk is equal to pk. So this third statement, third property, is trivially true for k equal to 0. Okay, that is the minor thing. That is for k equal to 0, it is trivially true, and for any k, 4, 7, 9, whatever, this is true for I equal to k. See, this thing has to be true for all k and all I less than equal to k, right? So two things are trivial. One is that for any k, I equal to k will be trivial, because by putting that we actually evaluate the update itself. Okay, and for k equal to 1, sorry, for k equal to 0, for k equal to 0, the only possibility for I is 0. Okay, So that is B1 Q0 equal to P0. That also therefore becomes trivially true, because there that is the only possibility. So now, and property 1 and property 2 cannot be talked of for k equal to 0. Okay, because if k is 0, then below that there is no scope of I. Here also, if k is 0, then there is no scope of I below that. So conjugacy, you can talk only about two vectors. Okay, with a single vector in hand, you cannot talk of conjugacy. So for k equal to 0, these two properties, the question does not arise, and this property is trivially true. And for any k, this property, third property, is true for I equal to k. So in the following, we will try to establish these two things for k greater than 0 and for all I below that. Okay, and this one we will try to establish for any k with all the I values below that. Okay, for equal we don't have to do that because that has been trivially settled. So for I less than k, the third property, the inverse Hessian construction property, actually we try to attack first to begin with. And there, since we are talking about a convex quadratic function with constant Hessian, so that constant Hessian, whatever it is, we don't know it, but some constant Hessian. So HPI equal to QI, we can use anywhere. So by using this property in this product here, this QI is replaced with HPI. And then as we open this, we get PK transpose HPI or its transpose. It's a scalar, so either way it is same thing. PI transpose HPK. Okay. Similarly, this. Okay. So in these two places, we can put that. So in these two places, here and here, we put that. Okay. And the rest is the same. Now, this shows that this is actually in the context of property 3. But this shows that property 3 equation will suddenly reduce if we first show property 1 and property 2. Property 1 is the conjugacy property, which will set this equal to 0, which is here also. And property 2 is the other conjugacy property, okay, between q steps, which will set this equal to 0 and therefore this equal to 0. Okay. And that means that if the properties 1 and 2, the two types of conjugacy properties, are settled, then this will be 0, this will be 0, this will be 0, this will be 0. And that means that this entire bracketed scalar product, scalar component, scalar coefficient, and this scalar coefficient will become 0. And bk plus 1 qi will turn out to be same as bk qi. That means that once we establish the two conjugacy properties, this whole thing will be gone, okay, for I less than k, and we will have this finally. That is, this equation will get cut right here, which will mean that over old steps, qi, I less than k, the new inverse Hessian estimate behaves exactly as the just previous one did. Okay, and that's a great advantage. So for k equal to 0, we have already covered the thing. Now for k equal to 1, the conjugacy property. For k equal to 1, only one I is possible, that is 0. So P0 transpose HP1. Now put things as you need. Now this P0 transpose H is symmetric. So that can be put together as HP0 whole transpose. And this P1 is actually alpha 1 D1. Okay. Now HP0 is Q0. So put it. Alpha 1, keep it here. This D1, by definition, it is minus B1 times gradient at x1, right? So now open this a little more. As you open this, put this minus here, and Q0 transpose B1 is actually B1 Q0 whole transpose into this gradient. Leave it here. B1 Q0 is already 0, the trivial step, right? So B1 Q0 not 0 but P0. B1 Q0 is P0 by the trivial step. So you put that P0 here, and now you have got this. And that means that P0 is the step along which a line search has come and converged at x1. So P0 and the gradient at x1 should be orthogonal, and that means this is 0. So this first conjugacy property is established for k equal to 1. For k equal to 1, the second conjugacy property, Q1 transpose B1 Q0. In place of Q1, you put HP1, and in place of that is from the definition, this one, and B1 Q0 is P0. The trivial step has been shown. So this Q1 becomes HP1. This B1 Q0 becomes P0. And now open it, and you have got P1 transpose HP0, which is actually the same thing. Okay, scalar, its transpose is the same. And so since this is 0, so this is also 0. Okay. Now, we argued this earlier that when these two things become 0, then these two, all these four become 0, and you have got B2Q0 same as B1Q0. And B1Q0 has been shown in the trivial step itself. Okay. So B1Q0 is P0. So this shows property 3 for k equal to 1. So for k equal to 1, only old direction possible is I equal to 0. For that, the first property, the second property, and the third property. Okay. Now, for k equal to 2, what will happen? Two old directions will be possible. Okay, for k equal to 2, I equal to 0 and I equal to 1. And that means here we will have two of them, P0 transpose H P2 and P1 transpose H P2. Here also we will have two of them, Q2 transpose B2 Q0 and Q2 transpose B2 Q1. Similarly, here also we will have two, B3 Q0, B3 Q1. B3 Q2 we don't have to show because we have already settled that. So for k equal to 2, these 6 things you evaluate and check. This is the first conjugacy property. These two should be 0. This is the second conjugacy property. These two should be 0. And this is the third conjugacy property. This should be P0. This should be P1. Okay. So check these things as an exercise to get the spirit of this entire derivation. What we do here is that assume all three properties to hold for k equal to m. And then we try to check that for k equal to L plus 1 and I less than L plus 1. Because for I equal to L plus 1, properties 1 or 2 do not stand. And for the third property, that case we have already settled. Based on that, the update was determined. Now, just 1 minute, I will take a little break and come back by the time you examine these steps. Well, so the first conjugacy property, Pi transpose H PL plus 1. Okay? Because now we are trying to check it for k equal to L plus 1. So check these steps a little carefully. H times Pi is Qi. So Pi transpose H is Qi transpose. PL plus 1 is alpha L plus 1 DL plus 1. Now DL plus 1 itself, now this alpha L plus 1 is taken outside scalar, and this DL plus 1, the direction is minus BL plus 1 into gradient at xl plus 1. In the next step, these two together are clubbed here, bl plus 1 qi transpose. And this is actually known from the induction hypothesis to be equal to pi. Okay, so that pi transpose is here. And what we do with this gradient is that we open this gradient as the gradient at xi plus 1 plus the gradient difference between I plus 1 and I plus 2, I1 and I plus 2. That is, this is basically gradient at I plus 2 minus gradient at I plus 1. Okay, plus the next difference, plus the next difference, plus the last one is gradient at this point. This is what we needed, minus gradient at xl, which will get cancelled with the next previous till this point. So this gradient we put as the gradient at xi plus 1 plus all the differences from that point up to this. Okay. Now this thing is pi, so we put pi transpose here into this plus the same pi here into, now all these q's we write as h into corresponding p. So h into corresponding p. Okay, and now this is 0 because a line search along pi has ended at xi plus 1. So the vector pi and the gradient at xi plus 1 are orthogonal. So this is 0. And these two are, all of these are 0 because these have been settled up to this point according to the induction hypothesis for k equal to L. Okay, so all of these are 0 and therefore this whole thing is 0, and that settles the property 1 for k equal to L plus 1. And this becomes then trivial because this ql plus 1 we split as h times pl plus 1, and this bl plus 1 into qi is known to be pi from this. Okay, the induction hypothesis for k equal to 1, k equal to L, all the properties are correct. Okay, so this becomes pi and this opens up like this, and when you open this you get pl plus 1 transpose h pi, which is the same as this, so 0. With these two things settled, we get in the two brackets in coefficients, scalar coefficients of this and this as 0 0 0 0 all four, and therefore this becomes equal to just this, which from the induction hypothesis is known to be pi, and that settles property 3. Okay, so that means the whole thing is correct for all k. Okay, on a convex quadratic function, and that means close to the minimum point for any function. Okay, so this will converge at most in n steps. Now the more important and more troublesome positive definiteness property. With bk as positive definite, we want to check that the bk plus 1 that we get is also positive definite. Okay, for any function, for general function, for every step. Okay, so this is a more general statement that we are trying to prove. Here we are not going to assume the Hessian to be constant, neither actual Hessian to be positive definite. Our inverse Hessian estimate is positive definite. Okay, so a positive definite matrix can be opened like this. Actually, any symmetric matrix can be opened like this. And in addition, if the symmetric matrix is positive definite, then the diagonal elements in this diagonal matrix lambda will be all positive, and therefore we can take their square roots, and then this thing can be taken as the square root of the matrix Bk. You can talk about the square root of a symmetric matrix if it is positive definite. Okay, and that is this. And in this basis, we express several vectors that we will need on the way. The x that we will use to check positive definiteness, that for positive definiteness of bk plus 1, we will get x transpose bk plus 1 x and try to show that to be positive for all non-zero x, right? So that is x. If you express that in this basis, then you will get some other vector, call it u, which will be non-zero because x is non-zero. Then qk, when you express in this basis, you call it v, okay, which is also non-zero because if qk had been 0, then the algorithm would have stopped. Similarly, the gradient, if you express in this basis, you call it w, which also will be non-zero because if the gradient had become 0, then also algorithm would have terminated. Okay, so keep in mind that x, qk, and grad of f at xk are now expressed in the new basis as u, v, w, and all of them are non-zero vectors. Then we check this for non-zero vector x. We want to check whether this is positive for any non-zero vector x. So whatever was the bk formulation, on this side we multiply with x transpose, on this side with x. And now what happens is that if you see that expression, then you will have bk plus first term, so it becomes this after the product x transpose on this side and x on that side. The other one was b pk transpose. So on the left side, as you multiply with x, it becomes x transpose pk, which is the same as this. On the right side, it becomes it you get pk transpose x along with it, which is also this. So it's square. Similarly, other terms you go on getting. This is a bkqk pk transpose and its transpose, those two terms. So that is why twice this thing. So from one side you will get this, from the other side you will get this. From both the terms you will get the same thing because the sum was symmetric. Okay, so whatever the left side of one gives, the right side of the other gives, and vice versa. So that is why the same two things you will get with C, and it becomes twice. Okay, and from the D part you will get this. This is D, and BK QK transpose BK. So half of it with X gives you this, half of this with X on this side will give you the same thing. Okay. So this is the whole thing. Now, this will tell you that this term is nothing but U transpose U, which is here. This will tell you that this thing is V transpose V, which is this. Okay. And this we will use later. This is in reserve for the time being. And then U transpose V will be X transpose BK QK, which is this, or Q transpose QK transpose BKX, same thing. Okay, so this one will be U transpose V. This also will be U transpose V. So those things, as you put, you get this as this as this, and then this one as U transpose V. Here in the denominator you get V mod square. Here it is U transpose V. So the things are a little simplified, okay, in terms of lots of mods, which are positive, very clear. We further do some simplification. All the C terms we take together, and therefore all the C free terms, that is all the terms free of C, we take separately. So C free terms will be this one and one term from here, 1 by this into this square, leave out this, and one term from here, that is 1 by V mod square into this, leave out this. The other two terms from here, this one, from here, this one, and this completely, they will be together on the right side with C related terms. So these two together we put and this separately. So this is the negative part from the last term, which we have put together with the first term. Second term remains as it is, and all the C related terms together come like this. Check this a little carefully. From here, you will get Q transpose Pk in the denominator. From here, this term. Okay. From here, the second term. From here, also the second term you are taking. So Q transpose P in the denominator you will get. From here, V mod square in the denominator you will get. So from here with C you will get V mod square, another V mod square will come from here when you add them together. So V mod to the power 4, Pk transpose X square, and from here minus minus plus, Qk transpose Pk, one from here and another from here you will come after you put them together, and this square. Okay. So that means the whole square, a square comes from here, b square comes from here, and minus 2ab comes from here. Okay, here both of them will come in the product. V mod square also will come, Qk transpose Pk also will come. So four things will be together. Okay, so when you put all of them together, you will get a square minus 2ab minus b square, which will become a minus b whole square kind of thing, like this. Okay. Do these steps on your own and you will be able to see how they assemble together. Okay. Now, is this positive for all x? A lot of positive things together are visible, except that about this Qk transpose Pk, we are not yet sure. Okay. So, because we have not checked it. So, let us check it now. Qk transpose Pk. So, which is same as Pk transpose Qk. So, Pk transpose Qk is the difference of gradients at these 2 points. And Pk transpose, this gradient is 0. Because along Pk, we have come to xk plus 1. And then this is the gradient there. So, line search ended there. So, that gradient has to be orthogonal to the direction. So, this part is 0. So, what is left is minus Pk transpose this gradient. Okay. And now Pk is alpha k dk. So Pk transpose is this. Okay. And gradient here. What is dk? Dk is minus bk gradient at xk. So in the next step, this minus and minus plus go out, and we open this and we get alpha k grad f at xk transpose bk this. That is this. Now you see, what is this? This is a quadratic form in which grad f is a non-zero vector. So this has to be positive, okay? Because bk is positive. In particular, we denoted root bk into this vector as w. So this entire quadratic form turns out to be w mod square. Okay? And this is positive because w is a non-zero vector, and alpha k is obviously positive. Okay? So you know that this is positive, and we can represent it as this according to our basis change. As we do that, then here you will have alpha k mod w square, and here also. So this comes as it is. This comes with this qk transpose pk replaced with this. And here a little more reduction is possible. Not very important, because otherwise also you could see that it is positive. Okay. So here this is alpha k, which we keep, and then mod w square mod v square. Okay. This also is mod w square. Okay. So we can put this mod w square v square inside the square root square sign. Okay, so inside 1 power of mod w and 1 power of mod v will go in the denominator. 1 power of mod v will cancel one of this, the other one will remain, and the other w mod will remain. That is why this becomes this. Here, 1 w mod will cancel this. Okay, 1 w. This is w mod square, and from here 1 w mod will come inside. Okay, because here is this whole square. So one of them will get cancelled, the other one will remain, and this v mod, one that comes in, that will remain here. So this, whether this is positive or negative, we don't bother. Whether this is positive or negative, we don't bother. Whether the difference is positive or negative, we don't bother, because this whole thing is a square. Okay, and alpha k is positive. So with, if you take c to be non-negative, then this whole thing will be non-negative. This is in any case non-negative, okay, because it is a square and this alpha k is positive. This is also non-negative because u transpose v is u mod into v mod into cos theta, where cos theta is the angle between the two vectors. And so this whole thing is u mod v mod, u mod square v mod square sine square theta. So this whole thing is positive, I mean odd zero. So this is together a non-negative term, this is together a non-negative term, and for c greater than or equal to 0, this whole thing is also a non-negative term. Okay? So with c greater than or equal to 0, which is an important condition, and hence phi also non-negative, greater than or equal to 0, we have here a sum of 3 non-negative terms. You remember when we studied Bryden's method, Bryden's family of methods, we talked about this phi greater than or equal to 0. This is the reason. Okay. Now, we have got a sum of 3 non-negative terms, which will be non-negative always. Can it be 0? It will be 0 only when all 3 of them together are 0. Is it possible? That is a question which we will next address. Can all 3 terms be 0 together? It's very easily visible that the first 2 together cannot be 0. Check. If this one is 0, that will mean u and v are collinear, and that will mean x and qk are collinear, because root over bkx was u and root over bk was root over bk qk was v. So if u and v are collinear, then x and qk are collinear. So that will mean that the x that we have picked up is a scalar multiple of qk. So if you put that, then you will put it like this: x equal to a scalar multiple of qk. But then the second term, which is this, will have, in place of x, it will have rho times qk. So this will become rho times pk transpose qk, which is the same as rho times qk transpose pk. Okay, and qk transpose pk is alpha k w mod square. Put that here, and then simplify. 1 alpha k goes off, 1 w mod square goes off, rho square remains here, 1 alpha k remains here, 1 w mod square remains here, and this is positive because rho is non-zero, because x is non-zero. Okay, alpha k is positive and w mod square is positive. So this whole thing is positive. So you are assured that first 2 together cannot be 0. If the first one is 0, the second one is certainly positive. And the third one will be non-negative as long as c is non-negative, or phi, whatever. The rank 2 update, therefore, will guarantee to maintain the positive definiteness of the inverse Hessian estimate. Okay? So if the previous one was positive definite, then the next one also will be. Rank 1 update is a degenerate case of rank 2 update for this value of c. and it may fail to maintain positive definiteness because here this thing may not be positive. Okay, so C here in the case of rank 1 update does not remain constant, and it is anyway not in our control. Okay, C or phi, and therefore this thing may not be positive always, and therefore rank 1 update does not guarantee positive definiteness continued over the iterations. In fact, rank 1 update has only one parameter in hand, so that all its attention is fixed at construction of the inverse Hessian correctly, and in that, after that, it has no freedom, and therefore it cannot allow any fudge around that to maintain positive definiteness. And it may happen that it may construct the inverse Hessian too early when the iterates have not entered the neighborhood of a minimum point, and therefore the correct Hessian and therefore the correct inverse Hessian may turn out to be indefinite. And that's why rank 1 update is not trustworthy. All rank 2 updates with non-negative phi will be all right. So for general functions away from a minimum, not much can be said about the nature of the actual Hessian. There may be also reasonable variation over iterations. Okay. Therefore, early construction of an accurate inverse is neither possible because there is frequent changes, nor desirable because that may not be positive definite. So therefore, it is well that rank 2 updates put the positive definiteness at a higher priority than correct inverse Hessian construction. And inverse Hessian construction gets done at leisure when enough iterations have passed and the steps are small, so the inverse Hessian remains constant over steps, more or less, and it has entered a zone of positive definiteness. So the conjugacy results show that these operate as you wanted. Okay. By that time, the accuracy aspects will become important, and then you will start getting the full benefit of Newton's method, because you are constructing inverse Hessian estimates quite correctly, but all the time positive definite. So you will get all the advantages of Newton's method without its trouble. So make note that this condition, which was a key point in our analysis of positive definiteness, gets ensured for exact line search. Okay? For inexact line search, how much inaccuracy you allow, based on that, it will get decided whether it turns out to be true or not. Okay. So, however, in most inaccurate line search situations, it turns out to be true, because as long as the point where you stopped your line search, there, as long as the magnitude of the rate of change of the function is less than the magnitude where you started, as long as that happens, this will turn out to be positive. There is no issue with that. Okay. So with exact line search, it is guaranteed. For inexact line search also, it holds most of the time. I mean, it will require a very crude, very inaccurate, extremely inaccurate line search and a very fussy kind of function to make it negative. But in principle, that can happen. Okay, so to summarize all the issues of this lecture, first, all rank 2 updates used in Quasi-Newton methods, as well as the degenerate rank 1 update, which is not used, okay, together form a continuous family of Hessian updates, inverse Hessian updates, and we formulated them from a general formulation together in one formula, right? And all these update formulae construct the inverse Hessian through line search steps and succeed in correctly estimating it in at most n steps, okay, for a convex quadratic function. And therefore, they help in enhancing the local convergence near a minimum point where the Hessian is more or less positively definite and more or less constant. And it also inherits all the properties of the conjugate direction method there. With this minor condition, the rank 2 update preserves positive definiteness over iterations if seeded with a positive definite inverse Hessian estimate in the beginning for any function, whether quadratic or not, whether convex everywhere or not. This inverse Hessian estimate will preserve positive definiteness all over the iterations. Okay. So here we stop, and this completes our study of unconstrained optimization. In the next lecture, we start with constraint optimization. Thank you.